Here, so we're continuing on with equilibrium. Should be chapter 13 still. And last time we really finished up sort of talking about, and think we did an example together of solving for the equilibrium concentrations. We use ice tables to do this. So when we're given either the initial concentrations, or again, you could also do this with pressures. As we talked about, if we do it with pressures, we do want to make sure that the units of pressure are in atmospheres. And the way that we go about it, as we talked about, is pretty much using an ice table. And again, ice stands for initial, change, and equilibrium. And really the purpose of the ice table is really to sort of find the change part. And that usually is represented by the letter X in this case. So when we have something like 2A plus, B goes to 2C, we would do an ice table with our initial concentrations, or again, pressures. So I'll just make up some numbers here, 4 molar, 4 molar. And as we talked about, in a lot of cases, they may not give you any information about reactants. So in that case, it is safe to assume that it is 0 to start with. It also means that if that is the situation, it's also safe to assume that this reaction is probably heading in this direction towards the product side. And that's important really for the change part, because that means that our reactant should be decreasing with time, while our product should be increasing with time. And the way we represent that in the ice table is minuses would then be on the reactant side, and plus X's there would be on our product side. The other really important thing when you do the change part is actually taking into account the coefficients in the balanced equation, because that really takes care of the stoichiometry, the mole-to-mole relationship. And if you don't do that, then you're going to be off. So in this example here, this would be like minus 2x, this would be minus x. And then on the other side there, we would have plus 2x, again, based off of the coefficients. And when we come to the equilibrium, we basically just carry everything down here. At this point, we go into the K expression. And, we put these guys in there. And that would equal, obviously, you would be given a K value, whatever it may be, 60 or whatever that number may be. At this point, you got to do some math, maybe the quadratic formulas. I think maybe we did in the previous example. That will be sort of the most difficult that we do probably in this class. And again, that is something like ax squared plus bx plus c is equal to 0. That correlates to x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a, where obviously that is where you get those numbers from. Also, if you do have a negative number there, or a subtracting of number, you keep the negative, obviously, when you go into the quadratic sort of formula. This will get you, as we talked about last time, basically 2x values. And one of them will not make sense. Now, you can, when you use the quadratic, get to positive numbers. You could actually get to negative numbers. You could get a positive and a negative number. So, whichever one will not make sense. And what I mean by will not make sense is basically when we do solve for the x, that x is pretty much all the x's here in our equilibrium line, which is ultimately what we're trying to solve for. And, if one of those x's, when you put it back in, usually will lead you to a negative number, then that is not good. So that would not be the correct x value that you would want to use in that case. And obviously the other one would be the correct one. So sometimes people think it's always the negative one, but it is possible in certain situations you could actually get two negative values, and one of them actually will still work, one will not work. So it's really when you put it back into that equilibrium line, if you do yield a negative with one of those x values, then not so good. When you do that and you do get the right x value, obviously that will then allow you to really get the values for everybody at equilibrium, which is typically what we're looking for in these calculations. We also talked about, since it really is math, once you get the equilibrium concentrations, if you have time, and probably a good idea sometimes, is to put it back into the equilibrium expression. And ideally, you should match the equilibrium constant value that is given to you in the problem. Should be fairly close to it. And it's a good way to kind of check your math, especially in some fairly complicated sort of math steps along the way where there's a lot of room for error. It's a good idea to stick it back in there and make sure you're kind of in the same ballpark as what it should be. Any questions on sort of ice tables and how to do it? All right, well, then let us do some. All right, so we'll start with this one. We have a mixture of 0.5 moles of H2 and 0.5 moles of I2. They're placed in a 1 liter flask. What is the equilibrium concentrations of everybody if the equilibrium constant is 54.3? Proceed, and then we will talk about it, and hopefully everybody will be on the same page. The idea to do an ice table in this class on a lot of things. So if you're ever in doubt, you could go wrong, I suppose, but it's probably a good idea. So here again, we're looking for those equilibrium concentrations. So we definitely want to do an ice table, which means we really do need some concentrations. In this case, we're given moles and liters. In this case, it's 1 liter, which means it's not too hard there to figure out our concentration of H2, which would be 0.5 moles divided by 1 liter. Gives us 0.5 molar for our H2. We would do a similar calculation here for our I2. And that would give us 0.5 moles divided by 1 liter. Gives us 0.5 molar. We could also write our equilibrium expression here for this guy, which would be our K would be the concentration of HI. And again, we do need to square it because of the coefficient, divided by the concentration of H2 times I2. And that is going to equal 54.3. Any questions so far? All right, so then let us go into the ice table. H2 plus some I2, 2HI. So initially here we have 0.5 and 0.5. Again, nothing mentioned about our products, so fairly safe here to assume that it is going to be 0. That also means that we could safely assume, as we've talked about previously, that this reaction should be going towards the product side there. And that means that our reactants should be decreasing, should be negatives, while our products there should be increasing and positives. So this would get us a minus x, and plus 2x situation. Again, making sure we take into account the coefficient there. That's going to get us to equilibrium of 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table there? At this point, we will go into our equilibrium expression as we had there on the previous page. 54.3, yes, I think. So at this point, what we're going to do is, again, take everything that's on the equilibrium line, put it into that expression, and then obviously solve for x. That would get us basically 2x squared up on top. That would give us 0.5 minus x times 0.5 minus x, going to equal our 54.3 at this point. Yeah. At this point, right, we want to make sure we take a look at what's going on. And if you look closely enough, it is a perfect square on both sides. You could do a giant square root and a giant square, or smaller square root, I guess, in that case. If you square root the left, you end up with 2x up on top and 0.5 minus x on the bottom. If you square root the other side, which honestly I usually forget to do, so 54.3 will give us a 7.3689. At this point, it's not much easier here to solve for x. We need to multiply what's on the bottom to the other side, right? And That would get us 2x is equal to, looks like 3.684 minus 7.3689x. We're going to bring our x to the other side, which is adding it to the other side, right? To combine our x values here. That should get us like a 9.3689x is equal to 3.684. Dividing our 9 to the other side there, or 9.3, divided by 9.3689, going to get us a 0.393 as our x value here. Any questions on that there? Could you have factored it out and did the quadratic? You could, and you should ideally get kind of the same answers. But, sometimes you might want to save some time, so you don't overlook some of those things. Now that we have our x value, a reminder that the x value that we just got is every single x that we see here in the table on the equilibrium line. That means that we are now able to actually solve for our concentrations. So that means that the concentration of H2 is equal to 0.5 minus x, which would be 0.393 in this case. That's going to give us 0.5 minus 0.393. Gives us a 0.107. I2 in this case is pretty much exactly the same. So 0.5 minus x, 0.107. And lastly here, our HI on the equilibrium line is equal to 2 times x, 0.393. That gets us 2 times 0.393 and 0.786 looks like. And again, that should be our equilibrium concentrations of everybody. Any questions on that? Again, we could check ourselves by putting those numbers back in, and you get something like 53.9-ish or 54-ish, which is pretty close, yeah. Say again, the 3 point this guy? Here? That came from multiplying the bottom to the other side. So basically it's 7.3689 times 0.5. Yeah. And then obviously we'd also multiply the x as well. Yeah. So basically we move that bottom to the other side and times everything in the parentheses by what's on that side. Other questions on that? So again, this is a different way to sort of solve it. And, like I said, probably a faster way than factoring everything out. You clearly can't always do this, but if it is a perfect square on both sides, don't overlook it and, give it a try. Any questions on that particular one there? All right, our big day of ice tables continues with another example. All right, if we got initial concentrations using the same equation and the same equilibrium constant there, what is the equilibrium concentrations of everybody? If this case we started with 0.00623 of H2, 0.00414 of I2, and 0.0224 of HI. All right, so take some time, do some math, make sure you know how to do it. I'll do it with you on a piece of paper. I'll try it out. I2, HI. Now, because they did give us really the concentrations of everybody, we really should look at Q, like we talked about the other day. Q, which is the reaction quotient, which tells us whether or not we are at equilibrium. And more importantly, in our case, if we're not at equilibrium, which way it needs to go to reach equilibrium. Now, what would that affect? Well, it may affect the actual change part of the ice table, right? We assume it's going to the product side in a lot of cases, and that's where our minuses and positives sort of come from. But if it was heading in the opposite direction towards the reactants, then, you would be actually decreasing your products and increasing your reactants. So whenever you're given all the information here, you do want to calculate Q just to make sure you're doing sort of your ice table correctly. So Q in this case is calculated the exact same way as we calculate K, which would be HI squared H2, and I2 here. Putting in the values that they gave us would give us 0.0224 squared up on top. And we got 0.00623 on the bottom and 0.00414 there as well. That gives us a Q value here of and looks like 19.4 in this case, if I'm reading my calculator correctly there. That means in this case, Q is less than or greater than K. It is less than K, which tells us we're not at equilibrium, which is probably not a surprise. Otherwise, this wouldn't be much of a question. But more importantly, it tells us it needs to go which way to reach equilibrium. It needs to go opposite of where that's pointing, so it needs to go to the product side. So now we can feel fairly comfortable when we do our ice table that this side should be minuses and this side should be positives when we do the change part. Again, if you had the opposite, that would mean that we would actually be losing our products and gaining our reactants, which would change around sort of the minuses and the pluses. So this sometimes overlooked by people in these sort of equilibrium problems. And this is really the second place, if you remember the other day where we talked about that, you could actually come across Q rather than just a straight sort of Q problem like we did previously. Any questions on that? So now that we're confident which way we're going, which is this way, we could go into our ice table here. So let us get this guy going. So we got an H2 and we got an I2 and we got a 2HI. So initially here 0.00623, 0.00414, and not to be forgotten over here 0.0224. So we do have an initial of that guy. Change is going to look very much like the previous one. This is going to be minus x and plus 2x. That means at equilibrium here, we got 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x in this case. Any questions on the ice table here? We can write our expression, which is the same one as the previous problem there, which will be HI squared divided by H2 and I2, and that is still equaling our 54.3. We're then going to put our equilibrium line into that, and that's going to give us 0.0224 plus 2x, which gets squared, divided by 0.00623 minus x and 0.00414 minus x, equaling our 54.3 in this case. Well, bad news is that is not a perfect square. Yes, so this is a math here. We got to do a little bit of factoring, FOIL method, whatever you want to call it. But basically, we got to do it to the top on the left, right, and also the bottom on the left as well. So I'm just going to kind of do those maybe individually here and then put them back together. So I'm going to start with like the top here. So looking at the top, we got 0.0224 plus 2x times basically itself there. And again, right in and out, right, to do it. And if you do all that good stuff, when you factor it, you do get something like 5.018 times 10 to the minus 4 plus 4.48 times 10 to the minus 2x plus 4.48 times 10 to the minus 2x plus 4x squared. Cleaning all that up, we end up with on top 4x squared plus 8.96 times 10 to the minus 2x plus 5.02 times 10 to the minus 4. So that's like our top part. Yeah. Any questions on that there? All right, so we're going to then kind of do the bottom there. So we'll do this guy in blue. So next we'll go to the bottom. It's going to flip it the page here to do that. We've got more room to write. So this is the bottom. And on the bottom there, we had 0.00623 minus x times 0.00414 minus x, again, in and out, in and out. And that is going to get us something like 2.58 times 10 to the minus 5 minus 1.04 times 10 to the minus 2x plus x squared. I'll just rewrite them together. So that would be the bottom here. I just basically added 0.00623 plus 0.00414 to get to this number here in the middle, basically. Yeah. Okay, now we got the top, we got the bottom. Let's put them back together here. So up there on top was, we had 4x squared plus 8.96 times 10 to the minus 2x plus 5.08 times 10 to the minus 4 divided by what we got above there, x squared, minus 1.04 times 10 to the minus 2x plus 2.58 times 10 to the minus 5. And that is going to equal 54.3. At this point, we need to take everything that's on the bottom right and multiply it to the other side there. So that means that everything that's up on top will stay there on the left. So up on the left there, we got 4x squared. Yeah. Where did I'm sorry, the 54.3? That's the equilibrium constant value. Is it? No, 19.4 is the Q value that we use to compare to the equilibrium constant to see which way the reaction was going. But in the actual problem, it's 54.3 is the actual equilibrium constant. Yeah. Other questions? Okay, so like I said, they're up on top, nothing is changing, so we'll just rewrite that there. Now multiplying the 54.3 to everything on the bottom there will get us a 54.3x squared minus 5.65 times 10 to the minus 1 x. And if I could read my writing here, 1.4 to the minus 3, 1.4 times 10 to the minus 3 there. All right, we're almost there. Now we need to combine everybody. Again, usually people keep the x squared positive, so that's what I'm going to do. So I'm now going to take everybody on the left-hand side and bring it over and combine to everybody on the right-hand side. Finally, once we do our combining here, that should give us 50.3 x squared minus 6.55 times 10 to the minus 1 x plus 8.98 times 10 to the minus 4 is equal to 0, which is our quadratic equation there that we need. Fun. I did it as well, you know, did it old school. Any questions on any of the math part? So clearly here, a lot of places where things could go bad. Even I did bad last time I did this problem. I subtracted my head and got the wrong answer. So don't do those things. Any questions on any of that? So this is now going to be our A, B, and C finally. So that is our A, right? That is our B. And that would be our C that we would use, obviously, in our quadratic of minus b plus or minus the square root of b squared minus 4ac divided by 2a. So I'm going to flip the page here and pop those numbers into that here. So that gives us x is equal to minus b, which looks like 6.55 times 10 to the minus 1, plus or minus, if you put in all the numbers in the square root before you square root it, you yield something like 2.48 times 10 to the minus 1, for which after you do the square root of it, you end up with 4.98 times 10 to the minus 1 divided by 2a, which gives you 100.6. In this case, we will get our two x values, doing the plus first, I believe. So doing the plus first will get us an x value of 1.15 times 10 to the minus 2. Doing the minus, so 6.55 times 10 to the minus 1 minus 4.98 times 10 to the minus 1 divided by 100.6 yields us a 1.56 times 10 to the minus 3. In this particular case, we yielded two positive values, which obviously could happen. One of them should not make sense. And when we look at the one on the left, which is basically 0.01, right? And we go back to our table, wherever our table was, there it is. Obviously 0.01 is larger than this number, right? And 0.01 is larger than this number, which means if we put that number back into our equilibrium line, that would give us negative concentrations, which is not a good thing. So in that case, we would not want to use this guy as it is too big and will yield you a negative concentration, meaning I'm hoping this should be good then at that point. Now we can go into the equilibrium line and solve for everything that we're looking for. So our equilibrium concentrations for H2 was 0.00623 minus x, so 1.56 times 10 to the minus 3. That is going to get us 4.67 times 10 to the minus 3 molar. Our I2 in this case, going back to the equilibrium line, was 0.00414 minus x, which would obviously be our x value here. And that would yield us a 2.58 times 10 to the minus 3 molar. And lastly, our HI from the equilibrium line was 2 times, no, actually we had a number there. So it's 0.0224 plus 2 times x. And that gave us 2.55 times 10 to the minus 2 molar. And those should be our equilibrium concentrations. Again, if we take those values and put it into our equilibrium expression, that would be 2.55 to the minus 2 squared divided by 4.67 to the minus 3 divided by 2.58 to the minus 3 gives us a K value of about 54, which is pretty close to 54.3. So I feel relatively confident I didn't screw up somewhere. Yes. So clearly, as you can see, a lot of places where you can mess up. So good idea at the end to put it in. And obviously, if you put those values back in and you get an equilibrium constant of like 5,000 and you had 54 to start with, you probably screwed up somewhere, I'm thinking, along the way. Any questions on any of those steps there? So a lot of math in this type of one to solve, a lot of places where you could go wrong. I would recommend, maybe breaking it apart like I did, kind of do the top guy, do the bottom guy. Just be careful when you put it back together that you put it back together correctly in the right spots and stuff like that. Any questions on this particular type of type problem? All right, our journey through ice tables continues with another one. If Kp is equal to 4.31 times 10 to the minus 4, we're looking for our equilibrium pressures in this case. If we started with 0.862 atmospheres of N2, 0.373 atmospheres of H2. Again, this is a Kp. Here we have pressures. We work it the same way. You could do, again, an ice table with pressures and Kp, so it works exactly the same way. So why don't you give it a try, see what you come up with. Let's take a look at this particular one here. So again, as I mentioned before, you could do an ice table with pressures. This, again, is a situation where we were talking about earlier that you do want to definitely make sure that the pressures are in atmospheres. And if they are not, you should convert them to atmospheres before you go into the ice table, just to make sure you get everything correct. So we will kind of roll through here like we were doing. So we have our N2 plus 3H2 giving us 2NH3. This will give us a Kp value of the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2. And that would equal our Kp value that was given to us, which looks like it is, I'll just put it down here, 4.31 times 10 to the minus 4 in this particular case. So we do approach the ice table just like, any of the other ones that we do here. We would take our initial pressure, which is 0.862, our initial pressure of H2, which is 0.373. And again, nothing was mentioned about our product guy, so we will assume 0 on that guy. Our change part, we will also assume it is heading in this direction since we have no products to begin with, will be minus x. That should then be minus 3x, and that should be plus 2x. Bringing us down here will get us 0.862 minus x, 0.373 minus 3x, and a 2x. Any questions on the table here? We will then put that into our Kp expression here. So that is going to get us, looks like 2x squared divided by 0.862 minus x times 0.373 minus 3x. And that also does need to be cubed because of the coefficient. And that would equal 4.31 times 10 to the minus 4. All right. Any questions up to there? Now, clearly, when we look at that, I see some cubed action there, and I think I should skip this problem and do a different one. Seems like the right idea. We probably don't want to skip this problem, and we probably don't want to do the math that's really involved in doing this problem here. So we want to kind of think about how we could solve this. And one thing that we can look at that could help us out in this situation is the value of Kp. Is the value of Kp a large value or a small value? It is a small value, right? And because it's a small value, when we reach equilibrium, would we mainly expect to have reactants or products? So it is a small value, which means it is products over reactants. So in order to get a small value, you need more products, less reactants, right? So we would expect reactants when we reach equilibrium. And that's a good thing because in this particular case, because of the equilibrium constant here, which is relatively small, we assume that we will mainly have reactants at equilibrium, which means will the change part be really large or probably fairly small? I feel like if I just keep doing like the hand motions here, there'll be an answer. So if we were going to mainly end up when this thing reaches equilibrium with reactants, is there a lot of stuff going to the product side? No, which means the change part should be relatively small. So in this case where we have a small equilibrium constant, we would expect basically the x there to be a relatively small number because it's mainly going to stay on the reactant side and not a lot of it's going to go to the product side. In this situation, we can make an assumption and we could assume that x is equal to 0 because of the small value that we have for k. Now, clearly here we cannot like zero out every x there, otherwise we have nothing to solve for. It is only the x's that you would be subtracting from a number or maybe adding to a number. But we cannot get rid of this x because frankly, we started with 0. So whatever we made is a lot compared to where we started with, as opposed to the other guys where we actually started with something and we're not going to make that much more. So what that will end up doing is leaving us 2x squared up on top. That will give us 0.862 on the bottom, 0.373 that also still needs to be cubed on the bottom is equal to 4.31 times 10 to the minus 4. That looks like a much more manageable type of the way to solve it. So let us actually then solve it doing this. So again, that gives us 4x squared up on top. That will give us our 0.862 and our 0.373 cubed, equaling our 4.31 times 10 to the minus 4. I'm going to clean up the bottom left there and then multiply it to the other side. So that's 0.373 cubed times 0.862. And then I'm going to times that by 4.31 to the minus 4. And that should give me, go that way. 4x squared is equal to 1.93 times 10 to the minus 5. So again, I kind of got a number here and then multiplied it to the other side. At this point, we want to then divide by 4 and also take the square root. So I'm just going to do both of those things at the same time. So here I'm going to divide by 4 and also do a little square rootage at that point. And that will give me a divided by 4 and a square root. That gives me an x value of 2.20 times 10 to the minus 3. Any questions so far on that there? Now, excuse me, do this. Okay, now when we do make this assumption, there are rules. We just can't randomly go about and start assuming zeros on everything, even though we may want to. There is a rule that we will use in this class. So there's a couple different ones, but we will use the rule that is basically referred to as the 5% rule. And what the 5% rule is basically once you solve for x, you then want to divide it by whatever you're going to subtract it from or whatever you were going to add it to and times it by 100. So if we were going to take our x, which is 2.2 times 10 to the minus 3, we were originally going to subtract it from this number here, which was our initial pressure of 0.862. We want to times it by 100% in this case. That gets us a 2.2 to the minus 3 divided by 0.862 times a 100. Looks like a 0.255%. Because the percentage is less than 5%, that means that our check here is good, and this is an okay x value to use. If you check it and it's above 5%, that means that the change is kind of significant, and you would have to then go back and solve it some other way, quadratic way, factor out the cube and do a quadratic formula, all that bad stuff. For our purposes here, since the quadratic will really be the hardest thing you'll have to do, you would have to go back and probably solve it using the quadratic formula. You don't necessarily have to check both. Usually if you check one of them and they're good, then they're both are good. You can check both, but usually, you know, like I said, if it's good for one, it's usually good for everybody. So since our check here was good, it's less than 5%, we can then use that as our X value, and we could put it back into our equilibrium line there. And that means that in this case, the pressure of N2 would be our initial, which was 0.862 minus X of 2.2 times 10 to the minus 3. And that would get us 0.862 minus 2.2 to the minus 3. Looks like, I'll call it 8.60 times 10 to the minus 1, and does in units of atmospheres here since it's a pressure. For H2, pressure of H2 is 0.373 minus 3 times X, 2.2 times 10 to the minus 3. That gets us 0.373 minus 3 times 2.2 to the minus 3, going to give us a 3.66, we'll call it, times 10 to the minus 1 atmospheres. And lastly, the partial pressure of our H, not HI, NH3. Going to be, should just be 2x, I believe. So it is just 2x, which would be 2 times 2.2 times 10 to the minus 3. Going to get us 4.4 times 10 to the minus 3 atmospheres here. Any questions on that? Again, we should be good if we throw it back in and sort of check it. Gives us, yep, about 4.6, somewhere in that ballpark. Any questions on that particular one there? Okay, so why did I not make the assumption on the first couple that we did, or the ones that we did previous to this? Could I have done the assumption on any of those that we did previous? The answer is no, right? And their answer is no, because our very first one we did the other day was an equilibrium constant of 7, which is a large value. So that means you should have a lot of products at equilibrium, and thus the change is going to be relatively big, while the other two that we did were 54.3 each, which means, again, a fairly large equilibrium constant, mainly products, and a pretty big change that occurs. So you can only do this with a small value of K, and you should always check it, especially as we go through the next couple of chapters. Will not always work. Will work in a lot of cases, but there are places where it will not work, and you will have to solve it a different way. So sometimes people forget about the checking part of it and just go with it. You definitely want to make sure that you check it. So we've now seen these type of problems where we could solve it with the quadratic formula. We've had a perfect square. We have a situation where we can make an assumption. Those really will be sort of the 3 ways it will solve these type of problems in this class. As I mentioned maybe the other day, another very common method is what's known as successive approximation. And basically what that means is we know the X value pretty much needs to be less than these numbers. So you kind of pick an X value and put it into your sort of formula here, leaving just like this X to solve for, and you solve for that X, and you keep doing that process until the number you put in and the number you get out is the same, which again, if you're really crappy at it, will be a long, long day for you, yes? So we won't do any of that, but you sometimes will still see it like solution guides and stuff like that in books, and sometimes people will sort of solve it that way. So these will be the 3 different ways that we will do these type of problems: quadratic, assumption, or kind of a perfect square. And any questions on how to do ice tables? Super important calculation. Like I said, pretty much every other chapter, it's all about ice tables, from lots of it and some variations on it. But this is the main type of calculation that we do for a very big chunk of this class. Yeah. So You are responsible to be able to write the equation and show the ice table work, yes, and not try to fake the math, which is very common. People will do, like, I think I'm supposed to like do this, this, but I really don't know what's going on. So you do need to be able to show all this work along the way. Yes. Any questions? Okay. That was our day of fun with ice tables. Yes, we will lay it up here since we've got a